Okay, good afternoon. So today our speaker is Umberto Maio, who's currently in Trieste, the Observatory. He's there since 2020. Before, he was a postdoc for several years in Germany at the Leibniz Institute. He was in Potsdam. He was Marie Curie Fellow before that in Trieste. And he started his journey with a laureate degree in astronomy here in Bologna. He's an expert on many things, but today will tell us about studying structure formation in connection with different dark matter models with simulations. Please, Umberto.
Yeah, thank you, Franco, and thank you everybody for being here and listening to my talk. Yeah, today I will talk about first structure in CDM and WDM. Can you hear?
Yes. Yes, yes.
Okay. Yeah, in particular, this study was motivated by the recent JWST early releases that have shown for the first time high-redshift structures deep in the first half giga-year or so. The main goal of this study is to understand essentially the nature of dark matter through these observations. In particular, this will be done by exploiting the high-redshift universe, which is essentially a unique window to understand dark matter nature. In particular, we will try to assess the formation epoch of the first object, if and when first structures had time to collapse, and in particular, what is the main driver of gas collapse, like H1 or H2 evolution in early halos, the role of the first stellar populations, of feedback effect, initial mass function, and so on, and all these embedded both in cold dark matter and warm dark matter universes. To do that, it's important to perform ad hoc numerical studies of the cosmic medium in the most general conditions. And this will be done by cosmological hydrodynamical chemical simulations, which try to resolve at least the primordial ISM and primordial star formation. What do we expect from high-redshift epochs? Well, we expect primordial environments characterized by small dark matter halos. As an example, at redshift 10, you expect a mass function, a dark matter mass function given by these standard formulas here. And these formulas show that most of the halos at redshift 10 are of the order of 10 to the 8, 10 to the 9, 10 to the 10 solar masses. And these halos usually are H-cooling halos, where H-cooling means that the virial temperature is greater than 10 to the 4 Kelvin. They are named H-cooling because the main driver of gas cooling at these temperatures is expected to be hydrogen. However, since in earlier epochs, halos are smaller, so we are talking about halos of the order of 10 to the 6, 10 to the 7 solar masses. In those cases, the virial temperature is smaller than 10 to the 4 Kelvin, and the main driver of gas cooling structure formation is H2, so hydrogen molecules. These hydrogen molecules will lead gas infall and star formation in primordial epochs with a number of rotational and vibrational transitions. And if you have metal enrichment from earlier or nearby structure formation, you will also have additional metal cooling in the gas at low temperatures. We are talking about temperatures below 10 to the 4. At these temperatures, the main atomic coolants are essentially carbon, oxygen, silicon, iron, with carbon plus being the most relevant atomic coolant at all epochs, essentially. For understanding and for having a complete picture of the primordial epochs, therefore, it's important
to... Sorry to interrupt you. Are you changing slides, or is it still supposed to be the first slide?
No, I'm changing slides.
Oh, well, okay. Then we are still stuck at the first one. There were a lot of concepts there, so I was wondering if you were explaining them, but
okay, maybe. What do you see now?
now we do, but we were stuck at the first slide and I was hesitant to interrupt you, but okay. So we missed the second and the third slide.
This is the second. Can you
Yes.
see the third?
Now we do. When you went full mode, we didn't see anything changing. Try again. It was stuck somehow.
Now what do you see?
We see the plot of H and H2 cooling. Try to go back and forth just to be sure.
I'm going back and forth.
It doesn't change.
Okay, I keep this.
I think to share the full screen and not only the keynote presentation.
So stop sharing and share again.
Yeah, share the full display.
I'm sorry, I can't.
Guardate di qua così vi vedono. No,
No, I can't. If I go full screen, I have to exit from the full screen to share the full presentation.
But when you share your presentation, are you sharing just keynote or are you sharing the desktop?
I'm sharing a keynote presentation.
You should share the desktop.
Share the desktop, yes.
Enter the full screen.
Share screen.
Yes, now you should go full screen.
Yeah.
Yes,
Okay, now we can see the transition. Okay, okay.
So now you see.
So
Do you see the slide?
yes, we see them changing now.
Okay. So where was I?
Slide 4.
Here, right?
Yeah.
So yes, to study the primordial epochs, therefore we need a number of ingredients to be followed during gravity and hydro calculations. First of all, we need to understand and to follow molecular evolution, because molecules, in particular H2, in the gas phase, determine the very first gas collapse event. Then, after these first episodes of star formation, we have metal enrichment. Therefore, metals determine the following structure formation events, the second generation of stars and galaxies in general. And of course, we need stellar evolution, because from stellar evolution calculations, from the INAF, supernova yields, and so on, we determine the amount of metals and the time scales during which these metals are ejected into the surrounding medium. Okay, so in practice, you have to convolve all this within numerical simulations and include a number of reactions to address consistently molecular evolution, which is the most important ingredient for these epochs. And therefore, I have developed and improved over the years a chemistry network which can follow H2 formation in a detailed and consistent way for all the gas particles and the gas parsers, including a full non-equilibrium treatment. This means time-dependent treatment, all the main H2 channels for H2 formation, dust grain catalysis, photoelectric heating, cosmic ray heating, gas self-shielding, the impact of UV background, and so on. So I will not bother you with all the details of these calculations. The only important thing which I would like to stress is that in this kind of calculations, there is no H1 to H2 partitioning recipe adopted. I'm saying that because usually H2 is not commonly computed within numerical calculations, and there are partition recipes to determine whether there is H2 or not in a given gas phase. In my case, time-dependent H1, H2 abundances are computed for any given input gas density, temperature, and metallicity in each time step. This allows us to have a picture of the primordial gas, which is going to be visualized in these shapes here. You can see the primordial network. Here we are around redshift 10. This primordial web is characterized by high density neutral gas, these white regions and these spots in which molecules will form and will ignite structure formation. First star formation and then galaxy formation. Following that, once stars are born, you have metal enrichment from the different channels. And as you can see from these panels, over time, metals are produced in the universe. Supernovae type 2 are responsible mainly for oxygen production, while supernovae 1A are responsible mainly for hydrogen, the iron peak elements. And this is a simplified sketch of what of how the universe would get enriched over cosmic time. You can also appreciate in these panels that some elements like oxygen, for example, appear in the universe much earlier than others. For example, in this case, I'm showing iron because iron takes longer to be produced. Now, once you have all these things set, you would like to check if you are able to reproduce some of the gas quantities that are usually observed. For example, one of these are omega neutral, or if you want, omega H1 and omega H2. On the left panel, I'm showing, on the top panels, I'm showing omega neutral for a number of models and parameter variations, which I did in the simulations. And you can see that in general, omega neutral can be decently reproduced by the models with neutral fraction reaching almost the baryon fraction at redshift around 6 or so, which is when the universe gets reionized. Below redshift 6, most of the hydrogen, most of hydrogen atoms are ionized, and therefore only a residual fraction contributes to omega neutral, which corresponds to a value of about a few 10 to the minus 3 or so. You can do the same check also for omega H2, and these are the results in the bottom panels that you would obtain for different modeling, as I said, and different parameters. But in general, if you look at the bottom left panel, where I picked the two most interesting models, you can see that you can roughly reproduce the main available data at the moment, below redshift 6 or so. And these data are essentially ALMA data, VLA data, FIBS, COZ, aspects, and I mean all these data which came up in the most recent years. Just to give you an idea, only a few years ago we had these upper limits shown in a redshift between 2 and 3 for omega H2, and these upper limits were constraining omega H2 within more than 2 orders of magnitude, while nowadays we have much more tight constraints, mainly from ALMA at redshift higher than 2 or 3. Then once we have done these calculations, you can obviously compute the corresponding depletion times, which is essentially the mass of the gas divided by the star formation rate. And also for the resulting cooling times, you see that in general, both hydrogen depletion time on the left and H2 depletion time on the right agree decently with the observational constraints. What is interesting here is that in general, early depletion times are relatively short, in the sense that H2 depletion times are always below the Hubble time and of the order of 1/10 of the Hubble time, even a redshift 8 or higher. So this means that H2 is always leading gas cooling and gas collapse, even at very early epochs, even in the first half gigayear. If you would look only at H1, you will not see this trend. You would find challenging to explain structural formation at redshift higher than 5 or 6, while this can be avoided by H2. In practice, H2 is the relevant quantity to look at to understand primordial structural formation and early structural formation in the first gigayear. Okay. Once you have done all these checks for the cosmological model that you adopt, so far I have only considered the cold dark matter model, you can pass even to alternative models, in particular like warm dark matter models. Warm dark matter, as you probably know, is often advocated to solve small-scale problems of the cold dark matter, and this is done essentially by introducing a cut at high Ks, or if you want, a small masses, and therefore you get rid of small satellites, and you obtain fewer small mass objects. I have run my modeling on both cold dark matter and warm dark matter models with 3 keV cuts and 2 keV cuts. As an example, here you see maps for the cold dark matter and warm dark matter at 3 keV. The power spectrum that you would obtain with a 3 keV model is given in the upper left panel, this red line, where you clearly see the drop, the cut in the power for the warm dark matter models. The resulting dark matter mass function are obviously suppressed simply because in practice you put it at the beginning, the suppression in the warm dark matter power spectrum, and this is shown, for example, in the bottom left panel, in which the cold dark matter models show higher small mass values with respect to the warm dark matter models. In this lower panel, I show both the 2 keV and the 3 keV warm dark matter models, green and orange, respectively, and you see that there is a strong suppression for small mass objects. Okay. Okay, these are the preliminary tests that you can do on these different modeling and with the different assumptions. So now, what are the results? The results that you obtain are basically, for the star formation rate densities, are basically these ones. On the left, you see a standard basic cold dark matter model compared to the warm dark matter 3 keV models. So black versus red, and I plot both the total star formation rate density and the POP3 star formation rate density. You see that obviously the POP3 is always subdominant with respect to the total, but the amount, the ignition time of the star formation in the two models changes as a consequence of the variation in the power spectra. The ratio of this POP3 to POP2, the POP3 to total star formation rate density is roughly consistent below redshift 15, so they are more or less at the order of 10 to minus 3, 10 to minus 2% of the total, while at very early times, when POP3 are supposed to dominate star formation, you clearly see a gap, a delay in the warm dark matter models. In the bottom left panel, I'm collecting all the different models that I have run and comparing them to the to last year JWST determinations, essentially. And you see that some of the models are not really meeting the observations. In particular, the 2 keV model is barely consistent with the points at redshift 13 or 14. And so this model would be put under stress by JWST early release. In these plots, I show also different resolutions and box sizes, but usually these do not impact dramatically the results. Then you can check some other observables like the stellar fraction as a function of the stellar mass on the left. The magenta shaded area is again the observational constraint given by early JWST data, and the different colors are the different models. As you can see, in general, all these models tend to have or to predict high mass objects within the observational constraints, both CDM and WDM models. Although the stellar fraction is slightly shifted for the different warm dark matter models, with smaller star fraction in the 2 keV warm dark matter model, slightly higher in the 3 keV, and higher in the cold dark matter model. At the same time, you can check the UV luminosity functions. As an example, I'm showing you an example of the UV luminosity functions on the right panel at redshift 9. And as you see, again, JWST data seem to trace quite consistently predictions. We are in a regime where cold dark matter and warm dark matter have already converged, essentially. The differences in the luminosity functions are at UV magnitude lower than 15, minus 15 or 14, while for the JWST data, we are at UV magnitude of the order of minus 17 or high or lower. So we are below minus 17, up to minus 22, more or less. This means that it seems that the JWST data are in line with the theoretical expectations that we have, and actually we already had in the past, while warm dark matter models are still tricky to fully constrain with only this data. These plots, instead, the following one shows the faint UV correlation functions for the 3 models which I'm focusing on. I'm taking faint UV magnitudes, so I am around minus 12 for UV magnitude, and then computing the pairs as a function of the distance. And as you can see, the different models have different slopes. When I plot the correlation here, I'm essentially plotting 1 plus xi, where xi is the correlation property is said. 1 plus xi is the overprobability, if you want to call it this way. At high distances, at large d distances, all these functions converge to unity as expected by the construction, while the slopes of these correlation functions changes significantly, because we have a range from going from minus 1.3 for the cold dark matter model up to minus 2.6 for warm dark matter model. So the warm dark matter model with 2 keV mass particle has a slope which is a factor of 2 smaller, essentially. While in the 3 keV case, we have a sort of intermediate trend because the slope is about minus 1.7. This means that if you would ever manage to observe faint objects, you could discriminate warm dark matter from cold dark matter from the slope of these faint objects. Okay. In this case, I am plotting the results at redshift 9, but you can do the same exercise at higher or lower redshifts if you like. Once we said that, we can further explore, for example, other mass density parameters like omega star and omega H2. Omega star is essentially the stellar mass density parameter. And as I said before, this is vaguely similar to the star formation rate density in the sense that the 2 keV model is barely consistent with the data. although I have to say that this data at high redshift should be confirmed. In the H2 case, omega H2 on the left panel, you see that this magenta box refers to the VLA equals Z determinations. The cold dark matter models usually meet the box, while the 3K, well, also the 3KV model can reach H2 values close to the box, while the 2KV model is not able to justify such high H2 values. Well, high with respect to the 2KV trend, which is a factor of 2 below 10 to the minus 5 in practice. Then you can
maybe.
Sorry?
Let's say 3 more minutes or less.
I'm done.
Okay, perfect.
Just this slide and then I'm done. And then I wanted to show some another tool which might be interesting for dark matter determinations, which is the CO intensity at different halos at high redshift. If you check the CO expectations in these different models, you see that while at low redshift, where low means redshift 7, the trends converge. At high redshift, warm dark matter models predict scarcer distributions of points, while the cold dark matter trend is much more well established, well defined. This basically is a consequence of the fact that in warm dark matter you have a suppression, as I said, of the power and of the low mass structures, a delayed H2 formation, and a delayed gas collapse, star formation, metal enrichment. Once the halos have grown enough, the trends eventually catch up, and cold dark matter and warm dark matter keep having the same evolution. This happens because at redshift 7 or lower, in practice, baryon feedback dominates over dark matter assumptions. So this is the final slide of my talk. Yeah, I would like just to stress that the high redshift universe is a unique window to study the nature of dark matter, and has not been really exploited enough, I would say, because there are relatively few works in this redshift regime trying to assess different cosmologies than CDM. While the main results are listed here, so I will stop here. Thank you very much.
Okay, questions for Umberto. Also from home, we are not so many in presence here, like 4. Wasn't there Julia? Okay, she disappeared. Well, I'm first, but okay. Can you hear me now?
Okay. Yeah.
Okay, 1 second. I'm using, okay, the laptop. So one question, if I understand correctly, you say there was no surprise in finding high redshift galaxies in the models you just presented, that I missed if they were already there before or not, but the key was to have, say, to follow more properly all the various coulants, and you could form high redshift galaxies not in tension with JWST.
Yeah.
findings.
In practice, if you follow properly gas cooling, pristine gas cooling, you would explain naturally JWST galaxies at redshift 12 or so. And also you would explain the lack of strong, for example, dust content and the bright blue behavior of these galaxies. These galaxies are relatively blue, which means that they are young, star forming, and they haven't produced much dust yet.
Okay. And the key, I mean, if you have to name one ingredient, is it properly following H2, or is it just the more complex interplay of everything?
Well, no, I think that you would follow properly the gas evolution with molecular cooling and the ISM at a redshift. If you don't do that, you end up in a tricky situation in which in order to have something at a redshift, you will have to accept heating gas that forms stars. And this is not very reasonable. So,
okay,
just a second.
okay. Marco?
Yes, ciao Umberto.
Hey, ciao.
Good to see you. Long time. A question about the simulation. So do you expect any change or any difference if you do if you repeat your set of simulations with fuzzy dark matter, for example, which has a similar suppression to warm dark matter, but has slightly different dynamics?
I would expect qualitatively similar conclusions. One should check the details because probably the driver might not be the same, but one should check. Although qualitatively, I would expect the same conclusions. Yeah.
Okay, thanks.
Right.
Then Giulia.
Ciao.
Ciao.
I was just wondering about the cold versus warm dark matter, because I mean it's very nice that there's finally simulation of very high redshift of galaxies, but your models are, so the models you're using, which are the 3 keV is what everybody does, so no criticism. It's still now below many of the current constraints on the warm dark matter particle mass, which from joint constraint is 5 or even 6 at 3 sigma.
Well,
so I was wondering if you think that these are exaggerated or that they're not very accurate in
I don't
comparison.
know. Well, after JWST, there have been some studies that have put constraints at levels of 2.3 up to 0.6. So IGM, Lyman alpha forest, has suggests constraints around 3 keV. So, I mean, I think this is still a matter of debate. And at the end, it's just a parameter that you choose for this kind of work.
Sure, but I mean, the lensing or Milky Way satellites tend to prefer colder. So I was wondering if maybe it's in the simulations or there is some difference in the evolution.
Well, I mean, in the simulation, once you reach 3 keV or so, it becomes really difficult to distinguish warm dark matter from cold dark matter. So that's why many people, at least at high redshift, push towards 2 or even 1.5 keV, because you do see relevant differences. Once you reach 3 or 4 keV, then you are basically almost in the regime of cold dark matter. You wouldn't see much, and as a consequence, feedback effects would erase any signature immediately. But yeah, I mean, in general, it's true. Low redshift studies and Milky Way studies suggest higher masses, while IGM and high redshift prefer lower masses. Yeah.
Okay. Any other question? I don't see any, I guess. Okay. Therefore, that's it for today. Thanks, Umberto.
Okay, thank you.
Ciao, grazie.
Ciao. Ciao.
Tuesday.
Ciao.
Ciao. Ciao, ciao.